IT2103 Mathematics for Computing Logic. In this discussion, we are going to discuss propositional logic. Now, logic is the study of patterns found in reasoning. What we mean by reasoning is just thinking rationally. So, what we are going to discuss is logic and some of its applications and how to apply it. Central to logic is the definition of a proposition. A proposition is a sentence or a statement that can be specifically true or false. A proposition can be proved or disproved. To understand a proposition better, let us consider some examples of propositions. Let us take the first example on your screen. 2 is an integer. Now, we know that this is a sentence, and we also know that since 2 is an integer, this is a true sentence. Therefore, it is specifically true. Therefore, the sentence 2 is an integer is a proposition. Let us take another example. 2 is not an integer. Now, this is also a sentence, and we know that it is a false sentence. So, it is specifically false, and hence it is also a proposition. An interesting thing to note here is that a proposition need not be necessarily true. Now, let us consider another example. Is 2 an integer? Is 2 an integer? Now, this is a question, and although the answer to this question is yes, the sentence itself does not have a true or false value. Therefore, is 2 an integer? The question is not a proposition. Next, we take the example x is greater than 10, where x is an integer. Now, this is a sentence, but is it true or false? Now, the point here is that the true or falseness of this statement depends on the value of x. For example, if x is 1, then the statement is false. On the other hand, if x is say 20, the statement is true. So, though we have a sentence here, this sentence is not specifically true or false. It might be true or false depending on the different values of x, but we can't say at the moment whether it is true or false. Therefore, this sentence is not a proposition. Finally, we take the expression 5 plus 3. Now, here too it is obvious that this does not have a true or falseness to it, therefore, it is not a proposition. Now, we define the truth value. As we discussed, a proposition is a sentence that is either true or false, and this true or falseness of a proposition is known as its truth value. More specifically, the truth value of a proposition is either true or false depending on whether the proposition is true or false respectively. We can denote this true or falseness in various ways. For example, we might denote true by T and false by F, or 1 and 0, or simple T and capital F, or simple F. Here are some examples of truth values. Here are the two sentences we considered earlier. 2 is an integer. This has a truth value of true. The sentence 2 is not an integer has a truth value of false. Now, we come to an interesting concept known as compound propositions. Let us consider two typical sentences. 2 is an integer and 2 is a prime number. Now, these propositions just have one simple fact, and they are known as primitive propositions, or they are also known as atomic propositions or simple propositions, because they have one single fact. Now, what if we take these two sentences and combine them as such? 2 is an integer and 2 is prime. Now, this entire statement is also a sentence which has a specific true or false value. Therefore, the statement 2 is an integer and 2 is prime is also a proposition. This kind of proposition, where we actually build by combining smaller propositions, is known as a compound proposition. And we can build compound propositions from other propositions using words like and, which are known as logical connectives. We will be discussing logical connectives later on as well. Okay, so, more specifically, a proposition is said to be primitive if it cannot be broken down into simple propositions. Otherwise, the proposition is said to be compound. So, a compound proposition can be always broken down into a collection of primitive propositions. Okay, let us get back to the idea of logical connectives. Now, as we saw, logical connectives allow compound propositions to be built out of simple propositions. Earlier on, we saw and, as well as or and not are also logical connectives. Now, each of these logical connectives have various symbols which are useful for denoting them in mathematical forms. The process of AND is known as conjunction, the process of OR is known as disjunction, and the process of NOT is known as negation. Okay. So, now we come to the definition of propositional variables. A propositional variable is a variable that denotes a proposition. For example, we might denote the proposition 2 is an integer by p, or we could use q to denote 2 is prime. So, once we actually denote the proposition as variables, we can actually use them in expressions. What do you think this means? We know the symbol in the middle denotes AND. So, this statement as a whole denotes p and q, which actually means 2 is an integer and 2 is prime. Here are some more examples of propositional variables. If we denote it is hot by p and it is sunny by q, let us see how we can actually denote these sentences using variables. Let us consider it is not hot, but it is sunny. Now, we know it is not hot, so p is false, and we know it is sunny, therefore q is true. Now, notice though we say it is not hot, but it is sunny, this is almost the same as saying it is not hot and it is sunny. Let us consider it is both hot and sunny. We know q is true and p is true, therefore we denote it in this way. This is exactly the same as saying it is hot and it is sunny. Let us consider it is neither hot nor is it sunny. What this means is it is not hot and it is not sunny. We can denote it this way, not p and not q. This is the same as saying it is not hot and it is not sunny. Okay, let us get back to logical connectives. Now, what do we actually mean by logical connectives? Now, we will consider the example we considered before. Now, here is logical connective AND, which connects two propositions, 2 is an integer and 2 is prime. Now, we know that these two propositions it connects are both true. Therefore, the entire proposition as a whole is also true. Why do you say it is true? It is because the two propositions it is connected with are each true. Now, consider this example, 2 is an integer and 4 is prime. Now, we know that 4 is not a prime. Therefore, this statement, even though 2 is an integer, is true. When two propositions are connected with the AND and one of them is false, the entire proposition is also false. Similarly, 2.5 is integer and 2 is a prime is false, because even though 2 is a prime is true, 2.5 is integer is false. Similarly, when both propositions are false, for example, 2.5 is an integer and 4 is a prime, when both propositions are false, also the entire proposition is false. So, now this is actually the meaning of the logical connective AND. Similarly, we might consider the logical connective OR. Now, unlike AND, if two propositions are connected with a OR, the entire statement is true if at least one of the two statements is also true. So, in this case, the first three statements are all true and the statement as a whole is false only when both propositions it is built out of are false. So, we can actually define logical connectives more fundamentally and more formally using truth tables. The compound propositions built out of other propositions and logical connectives are also propositions, therefore, they too must have a truth value, as we saw. The truth value of combined statements built out of logical connectives can be defined using truth tables. Here is the truth table for AND. We see a column for P, we see a column for Q, and we see a column for P and Q. You would see on your left hand side that we have actually considered all possible values of P and Q, all possible combinations. So, we have two propositions and we see that we have 4 combinations. Okay, let us consider the truth values. When both P and Q are true, P and Q is true. In all other cases, it is false, as we saw before. Similarly, we can consider the truth table for OR. Now, in this case, P or Q is true whenever at least one of P and Q are true, and it is false only when both P and Q are false, as we saw earlier. Another logical connective we are going to consider is not. Now, unlike and or, which operate on two propositions, not operates on just a single proposition. We have P and then not P. So, pretty obviously, not P is true when P is false, and not P is false when P is true. So, if you observe truth tables of row and columns, and there is one column for each propositional variable and another column allocated for the final compound proposition. The table should also have enough rows to represent all possible combinations, that is true and false values of all the propositional variables. So, let us make a couple of observations. If the compound proposition has two propositions, as we saw in the truth table of and or, it should have 4 rows in the truth table. We got the 4 from 2 to the power 2, because that's all the possible combinations of true and false values. Similarly, if the compound proposition has 3 values, then it should have 8 rows, 2 to the power 3. So, we can make the general statement that if compound proposition has n propositional variables, it should have 2 to the power n rows, because all the possible combinations need to be represented. Okay, let us consider a general compound proposition and let us see how we can build a truth table for that. Now, we are going to consider the not of P and not Q. See, we have 2 not logical connectives and 1 and logical connective. The first thing we should do is represent all the possible true and false values of Q, all the possible combinations of the propositions. So, we have P and Q, and if you have 2 propositions, we have 4 combinations, and here are all those combinations: true true, true false, false true, false false. Now, if we want, we can actually go straight ahead and try to derive the truth values of this, but it's normally convenient to actually first write the intermediate steps before we come up with the final answer. Now, the intermediate steps are purely for our convenience. We don't really have to write them on the truth table, but it's actually easier if we actually write the intermediate steps before we actually come to the final answer. Now, we have a not Q here, so let's first find the truth values of not Q. We can simply derive the truth values of not Q by looking at Q. Once we've derived the truth values of not Q, we can get about coming up with the truth values of P and not Q. Here are the truth values of P and not Q. We actually derive these from looking at P and not Q. So, finally, once you have P and not Q, we just need to apply the not logical connective to that statement to come up with our final answer. So, here is our final compound proposition which we were going to find. Now, if you make a couple of observations, we see we have 2 propositional variables. Therefore, we need to consider all the combinations. Therefore, we have 4 rows. We have our final compound proposition in a column. So, we have 1 column allocated to that, and we have some intermediate columns. Now, as I said before, the intermediate columns are purely for our convenience, and it will make doing the calculation a little bit easier. Okay. Now, we come to a couple of definitions. A tautology is a compound proposition which is always true, or in general any proposition which is always true. For example, if you say take P and not P, obviously one of these 2 have to be true, therefore, the compound proposition is also true. So, we define a tautology as a proposition that is always true. Similarly, we can define a contradiction, for example, P and not P, as a proposition which is always false. So, there are just 2 definitions. Okay. Before we just get on to the next part of our discussion, let us just look at what we have talked about so far. Right at the beginning, we define what actually logic is. Then we defined a fundamental concept in logic known as a proposition. We define what the truth values of a proposition are. Then, using primitive propositions and logical connectives, we went on to build compound propositions. We define what the truth values of these compound propositions are using truth tables, and we actually define other kinds of compound propositions as well using truth tables. Finally, we spoke about something known as a tautology and also something known as a contradiction. Let us get on with our discussion. Next, we are going to define something called a conditional statement. A conditional statement is a mathematical statement of the form if P then Q. For example, if you consider if it rains then the match will be drawn is an example of a conditional statement. In logic, such a statement is denoted by P arrow Q. Note the arrow is pointing to Q. So, it intuitively looks like Q derives from P. If P is true, then Q is also true. Let us consider the truth table for a conditional statement. Now, this is rather interesting. Now, obviously, if we have a situation where P is true and Q is true, then the entire conditional statement is true. For example, if it really did rain and also the match was drawn, then the statement if it rained the match was drawn is also true. Now, if it rained but the match was actually not drawn, then the statement if it rained then the match would be drawn is false, because in actual fact it did not cause the match to be drawn. Now, those first two examples are pretty intuitive, but it becomes a little complicated when we look at the possibility what happens when it actually did not rain or when the P is false. Now, what actually happens here is if P is false, then we can actually give any proper view on Q. So, we have actually defined whenever P is false, we define the conditional statement as being true. So, the last two rows in the truth table are true. So, if P is false, then the entire statement is always true. If P is true, the entire statement is true only if Q is also true, and if Q is false, the entire statement is false. Similarly, we can define something known as a biconditional. A biconditional is a mathematical statement of the form P if and only if Q. For example, we can say if and only if it rains, then the match will be drawn. In this case, if the match is drawn, then it definitely rained, and if it rained, then the match will definitely be drawn. Now, unlike in the previous example where we said if it rains the match will be drawn, now if it really did not rain, then this statement definitely says then the match must not be drawn. So, in logic, a statement of this kind is denoted by P, a double arrow Q. Now, if you look at the truth table, a P biconditional Q is true only when P and Q have exactly the same values. For example, it is true whenever P and Q are both true, it is false when they have different values, and it is again true when P and Q are both true. Sorry, when P and Q are both false. Now, we can just briefly consider a different concept here on how to denote propositions. This is just about a convenient concept. Consider this compound proposition P and Q. Now, this proposition is actually a function of the propositional variables P and Q. So, like we define other function in mathematics, we can actually define this compound proposition as a function. For example, we might define it as capital P PQ or Q PQ or R PQ. Just note that the capital P here or the capital Q here has actually nothing to do with the propositional variables or the symbols used to denote the propositional variables itself. They are just symbols. For example, we can define a mathematical concept like this: f(g) is f plus g plus 2. Actually, this capital F just defines a function. It has actually nothing to do with the simple f here. So, that is similar to what we have actually done with propositions. So, this is a convenient notation. Now, using this notation, we could actually define the concept of equivalence. We say that two propositions, say for example P and Q, are said to be logically equivalent or also equivalent or equal if they have identical truth values. Now, if they have identical truth values for all combinations of the propositions, then they will have identical truth tables. Now, we can denote this by P and 3 straight lines Q. So, this actually denotes equivalence, which means that both these compound propositions have identical truth tables. Let us consider example. Now, not of P and not Q, and P implies Q, we already considered the truth tables of both of these. And actually, if we look at the truth tables closely, we see that for all values of P and Q, not P and not Q and P implies Q have all the same truth values. So, therefore, we say that not P and not Q and P implies Q are equivalent or we can actually denote it in this form. So, as before, if we actually denoted each of the compound propositions by functions, we can also denote it like this. Now, here are a couple of more examples of equivalence. P implies Q is also equivalent to not P or Q, and here's another interesting equivalence relation. We have P and Q or R is equivalent to P and Q or P and R, or we have P or Q and R, which is equivalent to P or Q and P or R. Now, these relationships are actually known as distributive laws, which we will be considering later. Here's another interesting example of equivalence. We have not P and Q is equivalent to not P or not Q. We have not P or Q is equivalent to not P and not Q. These are actually known as De Morgan's laws, which we will also be looking in a little while. Now, you heard a lot about this word laws. Now, basically propositions satisfy various laws, as we have laws in mathematics. The laws of propositional algebra are actually a collection of such well-known laws. Here's a first law, the idempotent laws. What this means, what this says is P or Q is actually equivalent to P, and P and Q is also, P or P is actually equivalent to P, and P and P is also equivalent to P. Then we have something known as the associative laws, which says that P or Q or R is equivalent to P or Q or R. Now, the difference between these two statements is that here we first evaluate P or Q, and in this example we first evaluate Q or R. But what the associative laws actually says is that both these statements are equal, therefore it does not actually matter in which order you actually evaluated the parts of the statement. Similarly, P and Q and R is equal to P and Q and R. So, these laws are connectively known as associative laws. Then we have the commutative laws. P or Q is equivalent to Q or P, P and Q is equivalent to P, Q and P. So, as you will note, these should probably be intuitive and maybe obvious. Now, as we have the distributive laws, which says that P or Q and R is equal to P or Q and P or R, and we have P and Q or R, which is equal to P and Q or P or R. Then we have the identity laws, which says that P odd with something false is equivalent to P, and P and something which is true is also equivalent to P. We have P odd with something which is true, which is equivalently always true, and P and something which is false, which is equivalently always false. Next, we have the complement laws, which says that P or not P is always true, P and not P is false. Then we have something which is not true obviously has to be false, and similarly something which is not false has to be true. Then we have something known as the involution laws, which says that not of not P is equal to P. It's like the concept of double negation. Finally, we have De Morgan's laws, which say that not P or Q is equivalent to not P and not Q, and then we have not P and Q, which is equivalent to not P or not Q. Okay, so that's it for the laws. Now, let us consider an interesting problem. If you consider this statement P or Q or R, how would you actually evaluate it? Would you first evaluate the P or Q like this, P or Q, and then evaluate the AND with R, or would you first evaluate the AND like this, first evaluate the Q and R, and then OR that result with P? Which would you first do? Now, if both these different ways of coming up with the answer for this, coming up with the same answer, then there won't be a problem, because if they came up with the same answer, it won't actually matter in which order we do the calculations. But the question is, do they come up with the same answer? So, what we could do is, we could derive the value of this using this method, and then derive the value of this method and see whether they are the same. To do that, we can easily construct a truth table. Here are the truth values for P or Q and R, where we first evaluated the P or Q, and in this case we have the truth table for P or Q and R, where we first evaluated the P and the Q and R. Now, as you would notice, these two compound propositions have different truth values. Therefore, this statement is actually different from this statement. Therefore, we have the problem, which do we consider? If we were given this, would we evaluate this or would we evaluate this? Now, we have a convention that we always evaluate the second. We always evaluate the AND before the OR. This concept or this convention is actually known as precedence. Now, what if you actually mean to have this meaning? If you actually mean to have this meaning, then you should not write this, you should actually write the brackets or the parentheses. These actually force precedence over one operator or the other. But if you actually don't have the brackets, for example, if you write it like this, what we would actually consider as the answer is P or Q and R, meaning that we first evaluate the Q and R, the AND. The precedence or the order of evaluation depends on the precedence of logical connectives. NOT has precedence over AND, and AND has precedence over OR. And as we saw before, if you want to have a different meaning, you could force your own precedence by using parentheses or brackets. The final topic we are going to consider in this lesson is the topic of arguments. Now, typically, an argument is a series of propositions, or we say premises, assumptions or hypotheses followed by a conclusion. In this example, we see if prices are high, then the wages will be lower. If prices are high or there are price controls. If there are price controls, then there will be no inflation. There is inflation, therefore wages are high. So, typically argument is a whole lot of propositions known as premises followed by a conclusion. If you notice, we have a whole lot of propositions known as premises, and based on these premises we come up with a conclusion. So, we might actually refer to these as premises or assumptions or hypotheses, or sometimes we might even call these facts, and based on what we know, this is actually what we know, we can actually come up with a conclusion, which is also a proposition. Now, if you look at this actually closely, you will notice there are single propositions all over the place. For example, prices are high is a proposition which we can actually symbolically represent using P. Then wages are high, we can call that Q. Then we have there are price controls, we can call it R. Then we have prices are high, which is actually repeated before, which we can denote by a P. Then again we have there are price controls, again repeated. Then we have there is no inflation, which we can denote by not S. Then we have inflation, which can denote by S, and finally the conclusion, which you can denote by Q. So, if we can actually look at this even more closely, we see that the propositional variables we saw are actually connected to form compound propositions. For example, we said the prices are high is denoted by P and wages are high is denoted by Q. This is actually if P then Q. So, we can actually denote this by P implies Q. Similarly, we can actually denote all these sentences using propositional variables. For example, the next sentence is P or R. The next sentence is P or not S, R or not S. The last sentence is S. And finally, the conclusion itself can be denoted by Q. So, if you actually look at the symbols, what this argument actually looks like is something like this. P implies Q, P or R, R implies not S, S therefore Q. Actually, denoting arguments in this symbolic form is actually convenient and easy. We can actually define arguments in various ways. This is how we define it here. We can also define it in some other ways, like for example this. First we have the premises and then a line and then the conclusion. We can also denote it like this on a single line. We have the premises, the symbol and the conclusion. Or we can actually define it using this symbol which you might remember from your O-level mathematics. We have the premises, therefore, the therefore symbol and then the conclusion. Now, actually with arguments, what we are really worried about is whether the argument is valid or not. Now, we say that argument is valid if the conclusion of the argument is true whenever all the premises are true. So, therefore, if all the premises or the facts or the assumptions are true, then the conclusion is true, then we say that the argument is valid. If argument is not valid, we say it is a fallacy. For example, if we have a whole lot of premises and the conclusion actually does not follow from the premises, then we say that the argument is a fallacy. Here is an example of argument. We will just take a very simple argument. We have P and P implies Q, therefore Q. Now, is this argument valid? Now, we can actually find out whether it is valid or not by using the argument's truth table. Here is the truth table. Now, we have P, Q and P implies Q. Here we have premise 1, here we have premise 2 and here we have the conclusion. Now, we need to check whenever all the premises are true, is the conclusion true. Now, we see that both premises are true only in this case, in the first line. P is true, P implies Q is also true. We see in this case that the conclusion is also true. So, what we see is that whenever all premises are true, we see that the conclusion is true. So, this argument is valid. Let us take another example. Let us take P implies Q, Q, therefore P. Here too we can use the truth table, and if we draw the truth table, it will look like this. Here we have the first premise, here we have the second premise, and here we have the conclusion. Now, we can see that all the premises are true in actually two cases, in the first row and the third row. We see in the first row that the conclusion is true, okay, so that is fine, but we see in the third row that although the premises are true, the conclusion is not true. So, we have a case where all the premises are true, but the conclusion is not true. Therefore, this argument is a fallacy. Now, when the number of propositions involved in argument is large, it is easy to construct the truth table. For example, in the previous case we had just 2 propositions, therefore, it was easy to construct the truth table because it had just 4 rows. But what if the proposition is the argument is more complicated? For example, in this case we have 1, 2, 3, 4 proposition variables. So, if we are actually going to find the truth value of this, we need a truth table with actually 16 rows, and then we need to evaluate all these compound propositions individually. This might be actually a bit of a problem. So, in such cases we can actually come up with the validity of argument by analyzing the argument and giving what we call a proof. Now, here is an example of an argument which we defined before, and let us see how we can actually prove it. Given P implies Q, Q or R, R implies not S and S, how can we prove that Q is true? Now, we know that all the premises are true. Now, if all the premises are true, supposing R was also true, since R implies not S, we know that S would be false. But we also know that S is true, therefore, R is false. Now, this is a simple argument. If R was true, then since R implies not S is also true, then S must be false. But we know S is not false, therefore, R has to be true. R has to be false because R cannot be true. So, using the fact that R is false and P or R is true, we can actually show that P has to be true, because one of P or R is true, but we know that R is false. Therefore, since R is false, P has to be true. So, we can argue that P also has to be true. And so, then we come to the next step. Using the fact that P is true and P implies Q is true, we can come up with the conclusion that Q is true, which is actually our conclusion. So, we have shown this argument is true by first supposing that all the premises are true, and then using that we have come up with the fact that the conclusion is true. So, this is what argument proving is. Argument is valid if when all the premises are true, the conclusion is true. So, we have assumed that all the premises are true, and using that we have derived the fact that the conclusion must be true. So, this is an example of argument proving, and this is more elegant and shorter than using truth tables. So, that is basically the lesson for this episode. We will just recap a summary of what we did. In the second half, we considered biconditional and conditional statements. We defined what we mean by equivalence, and using equivalence we define some laws of propositional algebra. We define precedents, we define arguments and how argument can be valid or a fallacy, and then finally we considered argument proving.